Introduction and welcome everyone. My name is Champagne Cunningham and myself, along with Tom Bile and Deborah Moore, will be discussing a literature review that was funded by the U.S. Geological Survey Southeast Climate Adaptation Science Center, discussing the needs of science regarding climate change and harmful algal blooms in the southeastern United States. This was funded by CCAS and has support from Tennessee State University and the Lower Mississippi Gulf Water Science Center. So if you missed our introduction, I'll give you another quick brief one. My name's Champagne Cunningham. Again, I'm a former USGS LMG physical scientist. I received my master's from Tennessee State University, where I worked with Dr. Tom Bile and Devin studying harmful algal blooms. And I am now a PhD student at the University of Memphis, still studying harmful algal blooms and microbiomes in the Diner Lab. Devin Moore received his bachelor's degree from Yale University and is currently a master's student in Tom Bile's lab studying harmful algal blooms and currently works for the LMG. And then Tom Bile is a biologist stationed with the U.S. Geological Survey, and he also serves as science faculty at Tennessee State University. A brief seminar outline. Today, we'll be talking about, or at least from my part of the discussion, I'll be speaking to you all about harmful algal blooms, cyanobacteria, and how the southeastern United States is vulnerable to harmful algal blooms. Devin will then discuss the three drivers of harmful algal blooms, and Tom finishes off by discussing the different models used to consider and research harmful algal blooms. So what is a harmful algal bloom? Harmful algal blooms are often referred to as HABs. Harmful algal bloom events are different from eutrophication. Eutrophication is usually caused by an influx of nutrients, throwing a body of water out of balance. The water chemistry is off. The introduction of this excess nutrient amounts can cause sudden rapid growth of aquatic plants and green algae. This sudden introduction of nutrients may also cause the rapid growth of algae, blue-green algae or cyanobacteria. These cyanobacteria and blue-green algae can produce toxins, which cause harmful algal blooms. Now, not all harmful algal blooms can produce toxins. It just depends on the species. And even for the species that can produce toxins, they do not always produce those toxins. Researchers trying to find out what specifically may trigger the production of those toxins. In some bodies of water, if no toxins are produced, they can still pose a problem for that ecosystem. The sudden growth of bacteria during their decomposition process, when they begin to die, uses up oxygen, causing dead zones, and this can lead to fish kills as well, not just the toxins produced by the harmful algae. These photos show photos of Tennessee State University's wetland. The photo on the right shows a flock of Canada geese swimming in a harmful algal bloom. This area of our wetland in particular is adjacent to cattle. So those cattle and the waste produced by the cattle provide a steady and constant flow of nutrients into this water. So harmful algal blooms are prevalent consistently on this wetland and can pose a problem to the organisms who live there and the cattle and livestock which are adjacent to the wetland. So, as I mentioned before, not all algae can produce toxins, but the one that do produce toxins produce these things called secondary metabolites. Depending on the species or the type of organism, different toxins may be produced. Organisms such as cyanobacteria or blue-green algae, commonly found in fresh water, produce certain types of toxins. We also have dinoflagellates, which are commonly found in marine systems, and chrysophytes, which are, depending on the system, can be freshwater or marine. Now, there's different types of toxins, and these different types of toxins have different potential effects on organisms. Microcystin, which is commonly produced by Microcystis, produces a hepatotoxin, which affects the liver. We have cylindrospermopsin, which is a cytotoxin and primarily affects the liver and the kidneys. And then there's anatoxin, which is a neurotoxin, which affects our central nervous systems or the nervous system of whatever organism has been exposed to it. And then saxitoxin, which is another neurotoxin, again, affecting our central nervous system. Lipopolysaccharides and skin irritants can cause contact dermatitis, rashes, inflammation, asthma. It just depends on the concentration of exposure from this particular toxin. So, For those of us who live in the Southeast, who have ever been in the Southeast, we know we have some rather extreme weather conditions, and that climate conditions over the past few years have been increasingly more drastic. The Southeast United States in particular has a lot of reservoirs, and a lot of these reservoirs are anywhere between 50 and 80 years old. This graphic here shows the location of a few reservoirs in the Southeast. The purple color means that these reservoirs are somewhere between 50 years old, and the darker the color, so if it's closer to blue, means that it's closer to 80 years old or almost even 100 years old. These reservoirs are out in the open and are exposed to our climate conditions and extreme weather events. The nutrients from surrounding areas can be washed into these reservoirs, providing nutrients for harmful algal bloom occurrences. So we have an extreme weather event. This can provide an influx of nutrients, increasing the likelihood that we'll see a harmful algal bloom event in this reservoir. On the flip side of things, if we have a flash drought or if we don't see a lot of rain or there's no rainfall events in the area for a given period of time, we can see a change in the stratification of a body of water, and this can lead to harmful algal blooms as well. Devin will tell us a bit more about this later on in the presentation. So we know the climate conditions are worsening the prevalence of HABs and that they're becoming more and more of an environmental stressor for ourselves and for the organisms that live in these environments. So organizations like the USGS, CCASC, and other shareholders and stakeholders are doing things to further understand the prevalence and to educate the public about the occurrence of HABs and the risks they pose to the general public and organisms. One Health Harmful Algal Bloom System provides a data summary or a publication about the presence of HABs, how many human associated illnesses occur, how many animals are affected by the presence of HABs. They also tell us about which states report HABs, especially for data in 2021, how many harmful algal blooms occur, where they're occurring, and then what type of environmental testing is being done to study HABs. Now, with the increase of events that support HABs and the introduction of nutrients and all these other things, more HABs occurrences are being reported. So we have our institutions and researchers studying HABs, but we also have our media outlets picking up the study of HABs and reporting out to the public about how harmful algal blooms are affecting our bodies of water and what bodies of water may be at risk. This article here in New York talks about how harmful algal blooms are found in dozens of New York water bodies so far over the summer in 2024, and we can expect to see the same thing to start occurring here in the Southeast. So I've told you about the toxins and how there's different toxins produced by different species of algae depending on the situation. How can you become exposed to these toxins? One route of exposure is direct exposure, and this can happen through direct ingestion of a toxin. In a lot of cases, animals in these systems have direct exposure or will ingest toxins from harmful algal bloom. For example, you go out to your state park and go out to a lake. You let your dog off the leash and the dog runs out to the lake, jumps in, has a great swim. While he's swimming around in the water, he ingests a few mouthfuls of water that have toxins from harmful algal bloom. This is an example of direct exposure through ingestion. In some extreme cases, toxins from harmful algal blooms can become aerosolized and be in the air. So while you're walking around your area that has been experiencing a harmful algal bloom, there's a potential for you to inhale aerosolized toxins. And then the final one is direct contact through your skin. If you decide to get into the water with a harmful algal bloom, or if you're like myself or Tom or Devin and you're a researcher and you're studying harmful algal blooms and you're collecting water samples, you may get direct contact to your skin and have a bit of contact dermatitis or redness on your skin from exposure to toxins. Many agencies and state agencies, federal agencies provide documentation and warnings for the general public about the risk of direct exposure to harmful algal blooms. So you may see a sign like this that says avoid contact with water in areas that may be potentially experiencing harmful algal bloom. Now, for another route of potential toxin exposure, there's the risk of biomagnification. In these situations, a harmful algal bloom occurs. It's produced by the toxins are produced by the algae. This algae is eaten by a lower level organism on our trophic levels. That organism is then eaten by a higher up animal on our trophic levels. So a snail may be eaten by a turtle, or a smaller fish may be eaten by a turtle. The toxins that are originally eaten by the snail bioaccumulate, and magnify as they move up our trophic level. So moving from a snail to a turtle, you're moving up our trophic levels, and the toxins originally eaten by that snail are biomagnified when they're eaten by the turtle. And the same situation may occur when a person eats a piece of shellfish or a clam that has been exposed to uh, a harmful algal bloom occurrence or event and has ingested a toxin. A lot of times, more in coastal areas, we may see warnings about paralytic shellfish poisoning, which is a type of biomagnification that occurs during red tide events. But we can see similar circumstances in freshwater events if you're going fishing and you're catching fish and then you come home and eat a fish that has been living in a body of water that has experienced a harmful algal bloom. So there is lots of research and literature and publications understanding the drivers of harmful algal bloom. They primarily focus on three drivers: the physical drivers, which includes things like climate change, hydroperiod, the geomorphology, and the temperature of the environments harmful algal blooms are found in. Our biological drivers include things like changes in biodiversity of a system or the algae found in a system, the biogeography, so where these algae are being found, and the adaptive ability. And finally, our chemical drivers, which are things like changes in water chemistry, the nutrients available, and any potential pollutants which may also be found in these bodies of water. Research like this is being done with the USGS and at Tennessee State University as well, and in labs all over the country. Now, in addition to this field work and lab research, there is research also being conducted by institutions and universities to improve the models and predictions of monitoring HABs and predict when they will occur. And this is important research as well to predict when an area may be most vulnerable to a harmful algal bloom. And then finally, we are also seeing improved management and mitigation of harmful algal blooms. So how can we prevent a harmful algal bloom from happening? And in the case that one does happen, how can we mitigate the effects of a harmful algal bloom and then protect the organisms and people who rely on? So the USGS and others have put together several resources into real-time monitoring models and developing these real-time monitoring models to understand the drivers of HAB events, when they're going to occur, and then what ecosystems and environments may be affected. There are QR codes for both of these documents on this slide, so please feel free to scan the QR codes and learn more about the continuous monitoring efforts that are happening all over the United States about to monitor HABs and what may be causing them. So the United States Geological Survey also has HAB working groups. It's an interdisciplinary science approach to understand HABs. And this team addresses multiple topics. So things like what are beneficial and detrimental functions associated with cyanobacteria, what processes may drive toxin production and release, as this is a very widely studied topic, but it's very unknown what causes the process of toxins to be released. And then how can USGS provide knowledge and models to support early warning and mitigation efforts studying HABs? So now Devin will take us through the drivers of HABs and HAB development, and I will stop sharing so Devin can take it away.
Okay, thank you. Let me start sharing. Okay. Thank you. As Champagne said, I'm Devin Moore, and I'll be going through the drivers of HAB development. They're split up into three categories: physical, biological, and chemical. Physical changes could be things like a flood, a drought, raise or drop in temperature, whether it's the growing season or the dormant season. Different things in the abiotic environment. Biological changes are changes in the biotic environment. This could be introduction of a new species, introduction of a species of an invasive species that may thrive well in the competition. It could be a die-off, and there's an ecological role that's not being filled because a species is absent. Um, and chemical changes or changes in water chemistry, and they're closely correlated with physical and biological changes as well. Through we understand or we're growing an understanding of these drivers, how they affect HABs, and how they relate to each other through field work and lab analysis. Um, and better, or not better, developing that knowledge will lead to improved models and better prediction, which will in turn lead to improved HAB management. First one I'll be talking about is physical drivers. Um, as you can see, that's a pretty extreme flash flood in 2021. That city got 21 inches in 24 hours. And not only is the house flowing along, but you can see the color of the water. There's lots of sediments in that water, and in turn, lots of chemicals and potential nutrients in that water as well. On the right, you can see on the other side of the spectrum, we have a month-long drought from 2023. And while these are kind of opposite things, are on two sides of the scale, they have synergy and they both affect HABs, and they have synergy if they happen in succession, or they can have synergy. I use this diagram to talk a little bit about it. This arrow right here is this introduction of sediments would be what this looks like in the diagram. It's heavy rain comes in and pushes sediments into this body of water where there is a HAB, um, where there's a bloom. And if it's followed by a long drought period, then those sediments and nutrients are able to mix in the water, and the HAB is able to consume those nutrients and potentially grow past the point of equilibrium. And I'll get into some adaptations later that give some HABs the competitive advantage in situations like this. This just shows how climate change can affect um, physical, chemical, and biological can cause these physical, chemical, and biological drivers. If there's a heat wave that results in greater evapotranspiration, that may accumulate to a flash drought, causing plants to die and causing the soil to be less permeable. If that flash drought is followed by an intense storm, that soil in that state will wash away more, and it will cause more erosion. Those sediments will run into a body of water, and will be consumed as nutrient runoff and would promote plant growth, possibly have growth in that system. So as I said, this just shows how climate change and how a physical change can cause chemical and then biological change as well. Champagne mentioned stratification earlier, and thermal stratification will happen earlier in the spring and continue on longer into the year. There's the epilimnion and the hypolimnion. Um, the epilimnion is warmer, less dense waters on the top, and hypolimnion is below, colder, denser water. This is where there would be a more of a nutrient load. This is where more of the sediments would be. And a cool adaptation that some HABs have, that some cyanobacteria has, is it's able to change its buoyancy to maximize its resources. And so maybe at the surface on a sunny day, maximizing that sunlight, photosynthesizing. But when the sun goes down, it may change its buoyancy and drop to the hypolimnion and feed on some of those nutrients that are in the water there. When the sun comes back up, it may raise back up to the top. And so this is just a way that they have a competitive advantage in a way where um, they're, like I said, they're able to maximize the resources and able to maximize growth. And this is a diagram showing external inputs of chemical drivers. Lots of anthropogenic sources here. There's all of the pipes and things you see from the residential neighborhoods, the sewer networks, the stormwater infrastructure. Um, all of those things are inputs that end up getting into our water. And as well as some of these direct influences, there's also things like yard waste or just decomposing material that may find its way into a body of water. There's animal waste that may be a direct input through a pet or an agricultural area. It could be cattle waste getting directly into the water. But lots of times these external nutrients are getting the water through storm surges, through precipitation. So lots of them are storm inputs. This shows how this shows an internal input of chemical drivers. You can see down here, this is anaerobic sediment, and there is geobacteria in it. Once algae that's up in the system in the water dies off and drops some organic material down into the sediment, there is iron phosphorus in that algae. The geobacteria is able to interact with that iron phosphorus, give it an electron, and both the iron and the phosphorus become soluble and become available into that water system. And so there's no introduction of anything new. All of the chemicals are already in the system, and but they just weren't available to be consumed. And so This is the way that phosphorus gets into a system from already within the system. And this diagram just shows how this happens. There's the epilimnion, the hypolimnion, and then that internal phosphorus that was just freed up. As waters cool down in the day, the waters from hypolimnion or epilimnion drop down, and it actually pushes that phosphorus up to where the blooms are. And so it's able to be consumed more readily because of that process. I'll get into some of the biology of HABs. They're really, really unique. There are lots of different types of algae and lots of different types of cyanobacteria, and they have a wide variety of community responses to environmental factors. And so this makes it a little bit tough to have general studies because of the variation of responses, and also can make it tough to compare between studies. Um, they have lots of With the variety, they have lots of different adaptations that help them to thrive. Certain cyanobacteria can fix nitrogen, and so the only thing that they would need, the only limiting nutrient that they would have is phosphorus. That's the only thing that they would have to look for out if they're able to fix nitrogen. Some love warm water. They're able to adapt, and some have more efficient photosynthesis. In Mammoth Cave, we've seen some species growing in areas where we didn't think it was possible due to small amounts of light and very low intensity, but it's able to grow there to much our surprise. And with the actual production of the secondary metabolites that are toxic, we actually aren't completely sure what the purpose of that adaptation is. We know that the effect that the toxins have on other organisms, but we don't know the purpose of the production of these metabolites. And HABs have been around for a really long time. Cyanobacteria has been around for billions of years. It was actually around long enough and prevalent enough in the world to about 3 billion years ago change the atmosphere from a ammonia and hydrogen based atmosphere to now a nitrogen and oxygen based atmosphere through photosynthesis. And this is the diagram just to show different places that HABs can grow and some of those adaptations. There can be benthic algae, which grows on the bottom. Periphyton grows attached to things. Planktonic algae, floats freely. And that planktonic algae would be, some of those have the adaptation where they can change their buoyancy, go up and down. Then there's also the adaptation where they're able to process different types of light and adapt to that. Some fix nitrogen, as I said, and only have to look for phosphorus in the environment. And there's also the special enzyme rubisco that makes photosynthesis more efficient that some of these types of algae have. And as I said, all of these things give different species a competitive advantage in their ecosystems. And now I'll be giving it to Dr. Tom Bile, and he's going to be talking about models. And so let me stop sharing my screen.
Okay. And thank you, Devin. Me in presentation mode. Okay. Thank you, Devin and Champagne. I'm going to pivot the discussion to models as part of our science needs when it comes to HABs. And I'm going to start with the simplest models, the conceptual model, and that's depicted here. It displays the parameters that influence the development of harmful algal blooms in fresh water, and it uses very generalized information. The conceptual models rarely include quantification, and they can be adapted to fit different physical settings or timelines, and they provide a good starting point for projects. I use them all the time as teaching tools, but they're not really suited for supporting long-term management decisions. For that, we need much more rigorous predictive models, such as statistical or mechanistic models. You got to realize that going from a conceptual model like this one to a statistical or mechanistic model can be very challenging. It requires skills in mathematics and computer programming, as well as as understanding the whole system. You really do need to know what's going on. The fundamental difference between a statistical model and a mechanistic model is that statistical models use large amounts of data to look for patterns that can be described with probabilistic equations and are not based on cause and effect mechanisms, whereas mechanistic models are based on understanding the mechanisms that elicit a response in the system. So let's shift to mechanistic models. A mechanistic model is built upon a detailed understanding of the drivers in the ecosystem, which can then be represented through mathematical equations. Mechanistic models compartmentalize the different parameters and allow the user an opportunity to change one or more of those physical or chemical drivers to see if those changes elicit a different response. For example, Devin mentioned algae and cyanobacteria growth rates in responding to internal or external nutrient loads, temperature changes, thermoclines, and other variables. A mechanistic model would allow you to change some of those parameters. For example, reduce external nutrient loads, and then you see if that would in turn reduce the growth of algae. So a mechanistic model allows you to test different scenarios to see what strategy works best at reducing the possibility of a HAB event. The drawback of mechanistic models is that they require very detailed characterization and understanding of a very complex ecosystem, which may not be practical or achievable with limited resources and time. In the example shown on this slide, Fennell and others did develop a mechanistic model using physical and biological parameters to describe eutrophication in the Gulf of Mexico off the shores of Louisiana. The model describes phytoplankton growth primarily as a function of nutrients delivered to the Gulf from the Mississippi River and the Atchafalaya Basin. They also applied bathymetry, temperature, zooplankton grazing, nitrification, and other environmental processes to show that the increase in biomass is not simply a product of nutrients, but also a function of the sediments and detritus and other things transported into the Gulf. Their mechanistic model was able to predict algal blooms in the Gulf with a correspondence coefficient of 64%, which is pretty good. By using such a mechanistic model, Fennell and others were able to look at different variables and determine the cause and effect. Let's now pivot to statistical models, and these are ones that apply algorithms to data sets to provide probabilistic results. Recently, statistical modelers have been applying machine learning and artificial intelligence to identify trends and predict potential patterns in HABs from large data sets. An important trait of statistical models is that the outcome is based on correlation patterns and not causality. Another consideration is the output from statistical models is often bound to their calibration range, and the predicted results can then be limited by the data breadth from which they have been calibrated. For example, keep in mind that climate change is pushing our extremes. It is pushing physical, chemical, and biological boundaries beyond our historic records. So that means that if we're trying to predict out too far in the future and we know that the temperature is going to be a lot higher, then we're out of our calibration range. I mentioned that statistical models do not show cause and effect. However, some statistical modelers have been very intentional about trying to identify the cause and effect mechanisms by using multivariate approaches to determine which parameters have the greatest influence on the development of HABs. Another issue to consider: the types of data used in statistical models vary from one study to another, and that makes it difficult to transfer a model from one watershed to another. Those parameters may do a good job of predicting eutrophication in a Tennessee lake, but not necessarily apply to a situation in New York. While conducting the literature search, we found eutrophication models focused on rain, temperature, and nutrient loads. And then we found other models that relied on land use, drainage basin size, bathymetry of the reservoir, impoundments on the river, how many, and chlorophyll concentrations, salinity, and other factors. They used all that to predict algae growth. The difference in the data that was used makes it difficult for us to compare those models and say this is the best one. In the long list of those potential parameters also reflects the very thing that Devin was talking about, the complexity of the HAB system, the whole idea of a HAB response. Despite the limited and different information used in statistical models, several studies have demonstrated great results using statistical models for their respective geographical areas and under their current climate conditions. They were able to predict HAB events with very reasonable accuracy, which is very good for, giving warning to the public about HAB events. So if one of our goals is to have a HAB model that looks years into the future, especially with climate change coming on, we need to also incorporate something like a general circulation model, often called global climate models or GCMs. The concept of merging a GCM model with other models is to develop potential future scenarios under different climate conditions and then determine if there will be a response. And others have done this for things outside of HABs. Gao and others, for example, combine climate models with hydrology and fire frequency models to establish the probability of drought conditions that would then foster forest fires under different climate scenarios. That's shown on the left here. And then LaFontaine and others integrated climate and hydrology models to predict stream flow and water resources in the southeastern United States under different future climate scenarios. Again, using multiple GCM outputs, they were able to describe potential climate conditions in the future. And then those climate conditions were used to calibrate the hydrology model that incorporated land cover, geology, and topography information. They used the USGS's precipitation runoff modeling system, often abbreviated as PRIMS, which is a deterministic distributed parameter process-based model system that can integrate with the different GCM outputs to simulate the effects of precipitation, air temperature, and land use on potential hydrologic conditions. The GCM PRIMS hybrid model provided a nice description of the potential stream flow conditions in multiple basins, and it was able to tell us things like what can we expect in drought duration, drought frequency, or magnitude, the rate of change, and the timing of that. So those are all useful pieces of information for a land manager. Let's pivot now toward using a hybrid model where we combine models to look at HABs. And Chopra has done this in 2017. He provides a very good example, and he linked climate models with a water quality model and a biological model to derive a potential HAB scenario. The first step was to use multiple GCMs that were downscaled to estimate potential hydrologic conditions in various regions of the United States. Next, they used the U.S. Geological Survey's spatially referenced regression on watershed model, otherwise known as SPARROW, to resolve potential land use and chemical drivers such as nutrient loading and thermal stratification. SPARROW estimated the nutrient loading under different climate scenarios. Then they added a biological model called Qualidad to estimate the growth of phytoplankton and HAB events. In general, this hybrid model estimated that there would be more HABs occurring in the United States, especially the Southeast. As Champagne mentioned earlier, there's a greater density of reservoirs in the southeastern United States, and that is one of the things that kind of loaded into this model. And that's why it is showing up in the Southeast as being more vulnerable. And especially, you know, when you consider those things, those drivers that we just talked about, thermal stratification, temperature, that is going to affect those reservoirs. Now, a reservoir manager can take action and reduce the internal nutrient loads. Of course, that depends on the reservoir system. So please don't go out and say that Tom Biles said to go dredge your reservoir to remove those internal nutrients. Everyone is going to be slightly different. Okay, well, let's summarize at this point. And I hope you understand that cyanoHABs are an emerging water quality hazard. In fact, the CDC has ranked it as the #2 water quality hazard in the coming 10 years. Others have ranked it #1. It's not really a competition that I'd want to win, but just know that it is emerging as a serious water quality issue. Now, when we were doing this literature review, one of the things we noticed was that there was a lack of large programs, of monitoring programs for urban lakes and ponds. And that is something that probably needs to be addressed. Climate change, we're seeing, has all the drivers. It pushes the physical boundaries, which in turn push the chemical changes, and that gives us a biological response. And all of this, I hope you appreciate, that is very complicated, and that what someone learns out in Montana or someplace like that is not necessarily going to directly fit what is occurring in the Southeast. But there are, of course, there are certain similarities. And then we spoke about the HAB models, the mechanistic versus statistical. I bolded the statistical because that is what most of us are using. We are, a lot of different agencies and universities are gathering a lot of data, and it's out there, it's available. And from those huge data sets, we can develop statistical models. And they're still good on the regional scale. They're for specific water systems, and they seem to be very good at predicting the close future if the HAB will develop. The need that we see, though, with climate change coming on is the development of the hybrid models. We would like to see the merging of the global climate models with some kind of hydrology nutrient model and a HAB model. And when we do this, we need to consider, are we talking about large systems or small systems? The Chopra example I gave you was for large water systems. So smaller systems, though, shouldn't be ignored because a lot of people enjoy fishing in small water bodies. The goal of all of this, though, is to come up with some sort of model that natural resource managers can use, and they can target then parameters that give them the best influence on HAB development. So I just want to mention that our report is coming out. I've just got an email today that it's in the very final stages of being formatted. So it should be out in about a month, and it will be online. And I guess we will take questions at this time if you have questions out there. Thank you all.